Recording. I'm Leonid Chekhov, professor at the mathematical department at the Michigan State University, and today I wanted to present something that slightly unusual for me as well. I must confess, I'm an author of about 100 research papers, but it's very seldom that I'm just giving talks or presentations for a general audience. So I wanted to make some sort of entertainment out of it. And well, we'll see. It's up to you to decide whether it will be successful or not. So just to start with, I will make small pollings during my presentation. So the first polling is very simple. So just tell me, basically, do you hear me? Just what? Oh. Okay, great. Everyone is hearing me well, that's fine. So this poll was successful. And now let me just proceed to the main part of my presentation. And for this, I will share my screen. So let me just give me 1 second. It will take just... Now you see the screen of my iPad. And here is the picture that I wanted to start with in my talk. So it will be about generally some sort of how we can address problems in mathematics and sometimes in physics if we just make some experimentations. So how we can, for instance, consider the geometrical shapes in physics and how we can observe them in our backyard. So imagine that we have a garden pool. You see that's of slightly interesting shape. And we pour some water, and this water actually presses the walls of this pool. Imagine that they're flexible. So sides are rigid, but joints are flexible. And what is actually the maximum, how we can, what we get at the end, what will be the corresponding polygon, or in mathematical terms, if we just again come back to this picture, how we can make the area of this polygon maximum for this small duck to have a larger space to travel inside this pool. So it's famous problem in mathematics. I will not touch it in many details, just to say that it goes down to ancient Greece, and then there was actually, then it came to India, and then it came to European mathematics. And basically today my intention is to present this in some as a sort of some play. So we often refer to the mathematics as some dull science, right? But it's actually quite interesting that on many occasions we come to right conclusions or wrong conclusions by trials and errors. This means by experiment. And usually when we are talking about experiment, we have in mind some other natural sciences like physics. But actually in mathematics, there is a huge field for experiment as well. Except that, of course, on most occasions, this experiment is not a real experiment. It's some imaginable experiment, or on many occasions, it's just computer experiments. But even in mathematics, I just wanted to show today that there is at least some room for more traditional experimentations. So exactly what we start with. So what is the idea? So of course, every experiment, every good deed start with some bright idea. As soon as we got the idea, likewise, I got the idea of this presentation like 3 months ago, and then I was preparing to it. Then we proceed to its realization. And realization can be very much different in physics. For instance, it can be a 10 billion project like a Large Hadronic Collider to explore elementary particles. Or, well, sometimes we need just something smaller, like this Scotch tape and a pencil. And this, well, of course, equipped also with an electronic microscope. But that was the tools used, say, by Game and Novoselov in Birmingham University to invent and explore properties of a new material, graphene. And it's resulted in the Nobel Prize of 2010. So this means that not always we need huge machines to make some relevant experiments. So let's come back to the problem that I wanted to present today. So again, let's formulate it in more precise terms. Again, it's very much related to a practice. So how we can construct a figure of a maximum area? If we know, if we fix, say, the length of sides of this figure, or how we say the sum of this length is the perimeter. And again, it's a famous problem known for centuries, if not several thousand years. And well, again, it's very much practical. For instance, having a fence of given a length, like we have a fixed funds to buy it, how we can make some sheepfold of maximum area for our sheep to have a maximum area to walk inside. Again, if it's rectangular, we know that the maximum area, like we can solve it, it's just a problem in first year calculus, that the maximum area among all rectangles is presented by a square when the lengths of sides are all equal. And correspondingly, even if we fix this square and we bend it like that, it doesn't help, because if we bend it and have some other shapes, then they have a smaller area. So basically, we say that this polygon, or this corresponding square, it solves the problem of optimization. So constructing a maximum area fold among all possible folds, well, with a given perimeter. But imagine that it's not that this is just as any polygon, not necessarily square or rectangle. How we can characterize the shape that is winning if we fix the corresponding sides? So I propose to use a physical intuition. Again, if we come back to this picture from which I started, my presentation. So we know that water occupies the maximum volume. So if we imagine a polygonal garden pool with movable sides, when we pour water, it will automatically take the shape we are looking for. Well, we don't have a garden pool with movable sides. Instead, we imitate it by biotube and plastic tubes wrapped around this tube. And here I prepare just really an experimental presentation of this, because of course it was pre-recorded. I cannot do it right here, but it's in the same place. So let's start. Stop. Well, you see, not always experiments works well. I want to make a sound available. Let's try. Let me do it slightly differently. So I have it here, and I share my screen on my computer. I think. Mathematics in action. We don't have a garden pool. Instead, we imitate it by a simple device, you see, that I prepared using just a bike tube and several plastic tubes. And well, that's my secret, how I put them inside one another. And well, we want to imitate the same process as we possibly expect from the water that is poured down here, because it's actually pressed on the balls, and it's pressed in some precise way. So this figure actually takes the maximum area, because water, yes, water is just the law of nature that it's trying to occupy the maximum volume. And again, so I will not pour water here. Instead, I just pump this tube. So we actually imitate the same process of pulling apart these sides of this polygon. And well, and you see, before it's inflated, I can freely move it around. So there is no particular shape. However, if you do it, and let me do it, and during this process also you see that I specifically prepare some pattern here, a pattern of concentric circles. This is not occasionally, because somehow again we're a little bit cheating. We know the answer that we want to get at the end. Okay, so now it is inflated, and it's now much more rigid in shape, and I won't try to fit it into this pattern. So again, it will usually take some efforts if we don't know a priori where to, what will be the result. But actually, so if we did it correctly, we observe that if I follow some circle here, this circle actually, you see, it almost, well, hits or almost hits, okay. So it's, nothing is perfect. Nobody is perfect. So it's almost hit all these vertices of the corresponding polygon. So it's not just some polygon. It's a polygon with very precise feature that this polygon can be inscribed into a circle. And it's actually happened from mathematical considerations that for any original shape that we have, original shape, I mean the shape with which, in which this lengths of these sides are fixed. For each such shape, there is exactly one polygon that we obtain by moving and bending this shape around at these vertices, at joints, such that all these joints lie on the same circle. This is what in geometry is called inscribed polygon. Okay, so you see that indeed we got experimentally the corresponding pattern, and this pattern, now let's again make my picture available. So you see that this it's even you can see it's even better now, that we have a circle that hit all these vertices. So it's really inscribed polygon. And we have an explanation of it. We have a theoretical physics and mathematics explanation of this fact that we observe experimentally. Of course, we don't have time for that. If you want, you can have a look at the brochure that is available on the website. And well, experiment is never ending. Imagine that now I will ask you, given that we know this answer, can we make a homework? And it will be homework for you. So imagine that we have a parts of a fence like we did it here. So because we can say that this is the parts of the fence. Then with fixed lengths, and we can join them in any order. So what do you think? Will the maximum area of a polygon that we obtain using the same procedure and constructed out of these parts, will it depend on the order in which we join these parts together? This is something to think about. I will not tell you the answer. And just to conclude, so experimental mathematics is not a joke, actually. It's not the April 1st. It's a serious journal in mathematics. And of course, and it's a series, so it's about numerical observations and hypotheses. And so you see that some strong and original mathematical results are inspired by experimentation, conjectures suggested by experimentation, and data supporting significant hypotheses. So let me stop sharing my screen. And just the last poll that I want to make. Where is the list? Oops. So what can you say? Do you think that you want to learn more about experimentation in natural science, in mathematics, and will you construct this garden pool in your backyard? Okay. Good. Good. So it's almost done. So we have many participants, almost, and again, many of them vote for that. So I probably share results. That's fine. Thank you for coming. If you have questions, you can ask them using Q&A section. And well, again, thank you for your attention. Have a nice rest of your day. And well, goodbye.